Okay, so this is to rectify the mistakes that I had in the previous example, or on this the same example. Okay, so from the given figure of cable connection shown, determine the tension for all segments. Okay, so you have here your cable system having loaded with two concentrated loads. You have 3 kilonewtons at B and then 8 kilonewtons at C. Now, your cable system is supported by a pin at A and D. So basically, you would have here a vertical reaction at A and then a horizontal reaction at A. So this would be, let's denote this one as VA and then this one as HA. Same is true for D. You would have here a vertical reaction at D. Let's denote that one as VD and then a horizontal reaction at D, which is HD. Now, if we were to calculate for the resultant of those two pins, you would have here a resultant for A. Okay, let's denote this one as RA, and then resultant for D, this one would be RD. Okay, now if you were to analyze these points, okay, basically the only force acting on those points would be the cable themselves. Okay, so therefore you can conclude that whatever reaction that whatever reaction or value of the reaction on this particular support, that would be equivalent to the force acting on the members. Okay, and you can break them down into their respective components if you have your angle of inclination or your pitch for each inclined resultant force. Okay, so with that, we can start our analysis by taking the whole system as a free body. If you take the whole system as free body, let's say taking moment at point A. Why point A? Because basically at this particular part you have a complete set of data. By complete set of data, you would that means that you have here horizontal and vertical distances or difference in elevation, while on this particular side you do not have vertical distances with respect to a fixed datum. Okay, so with that, what we can do is to take the whole system as free body. You cannot calculate directly for VD and HT basically because you do not have, or what we can do rather, let me restate that one. What we can do is to calculate for tension at CD. Okay, so since you have a complete data, okay, as I stated a while back. So if you were to erase this one to expose the tensile force acting on that particular cable, you would have here tension at CD. Let's note that one as TCD. And then you can break that down into its horizontal and then vertical components. Okay, let's denote this one as TCDY, and then you also have your TCDX. Okay, for the pitch, you would have here 2 vertical, 1.5 horizontal. Getting the proportion, that would be what? That would be 4 vertical, 3 horizontal, then you have 5 as your hypotenuse. Okay, so with that, you can now have the whole system, or this part of your system, take that as a free body. Okay, so taking summation moment at A, summation moment at A is equal to 0. Let's take positive clockwise. On the clockwise direction with respect to A or about A, you would have 3 kilonewtons and then 8 kilonewtons as your positive rotation, and then you have TCDY and then TCDX as the opposite rotation. Okay, so starting with 3, you would have here 3, lever arm of 3 is 1. Next, you have plus 8. Lever arm for 8 is from point A, you would have there 3. And then minus for counterclockwise, you have TCDY. Lever arm for TCDY would be 3. And then minus, you have TCDX. Lever arm for TCDX is 4. Okay, that would be equal to 0. Okay, so transposing to the other side and then or manipulating the equation, you would have here TCD starting with Y, vertical component, that is 4/5. Lever arm is 3. and then plus TCD. Horizontal component is 3 over 5, and then lever arm is 4. That would be equal to, you have either 3 plus 24. Calculating for TCD. TCD is equal to 5.625 kilonewtons. Okay, now since you have now the data for this particular cable, you can now proceed your analysis to the next cable. Okay, so if you were to cut again the cable here, okay, exposing the tensile force acting on that particular cable, you have here your tension BC. Okay, next is we do not have any inclination for that one. Okay, so let's just assume that it would be inclined at an angle of theta with respect to the horizontal. Okay, so as shown in the figure, you can isolate take this as one free body. You would have your free body diagram for C. Okay, for joint C, you would have here joint C. You have your tension CD having a magnitude of 5.625 kilonewtons. Next is you have here your tension BC inclined at an angle of theta, and then of course you have your load. You have their 8 kilonewtons. Okay, so basically in this particular joint you would have two unknowns. You have your theta and then you have your TBC. Okay, but of course you can calculate for those since you have two available equations. Namely, you would have summation forces along X and then summation forces along Y. That would be equal to 0. Okay, so you only have these two available equations since you have a concurrent set of forces. Okay, so starting with summation forces along X, let's say that this is equal to 0. Let's take positive going to the right. Okay, so to the right, you would have TCD times, wait, let me write this down. Okay, you have here 3, 4, 5. Okay, TCD multiplied by 3 over 5. Then, minus, going to the left, you have TBC. Okay, times horizontal component, that would be cosine of theta. That would be equal to 0. So, TBC now, cosine of theta is now equal to, you have 5.625 multiply that by 3 over 5. Okay, so you have here TBC cosine of theta is equal to, you have 3.375. Okay, set that aside, equation 1. Okay, next, taking summation forces horizontal or along vertical rather along the y-axis is equal to 0. Let's take positive upwards. Okay, so on the upward direction you would have these two. Okay, and then on the downward you have 8. So upward you have here TCD, vertical component is 4 over 5. Next, plus you have TBC, vertical component is sine of theta, and then minus 8. That would be equal to 0. Okay, so calculating for TBC sine of theta, you have there, transpose to the other side, 8 minus, you have 5.625 times 4 over 5. So simplifying, TBC sine of theta is equal to, you have there 3.5. Okay? Equation 2. Okay, so if we were to manipulate equation 1, okay, equation 1 can be rewritten. Again, equation 1 can be rewritten as TBC. Calculating for TBC in terms of theta, you have the TBC is equal to 3.375 over cosine of theta. Again, that came from equation 1. Now substituting equation 1 to equation 2, you would have there 3.375 over the cosine of theta times the sine of theta. Again, this one, TBC, is to be substituted there, is now equal to 3.5. Okay, so sine over cosine is tangent of theta. Okay, sine over cosine is tangent of theta. That one is equal to 3.5 over 3.375. Okay, so with that, you can calculate for theta. You have their value for theta is 46.0416 degrees. Okay, next, so since you have now value for theta, you can calculate for TBC, or tension for BC. That one is equal to how much? That is 3.375 divided by the cosine of theta, which is 46.0416. Okay, so you have here TBC is equal to, that is 4.8621. Okay, so that would be in kilonewton, the tension for BC. Okay, next. Now, since we have calculated for TBC, okay, again, we have here the value for TBC to be equal to 4.8. Let me write it down here. TBC is equal to 4.8621. Okay, and then you have theta to be equal to, you have there 46.0416 degrees. Okay, so with that, you can have now the next joint, or the next segment. If you erase this one to expose the tensile force acting on your member. Okay, so let's have another color for this one. You have here tension AB. Okay, so tension AB is inclined with respect to the horizontal. Okay, just like the previous case for TBC. Now let's denote this one as alpha. Okay, now you have here theta, that is with respect to the horizontal. Now if we try to transfer to B, basically this one is also theta. Okay, so you may have that one as your free body now. Okay, so free body diagram for B. Okay, so let me rewrite that one. You have here TAB, you have your joint, and then you have your load, which is 3 kilonewton. Now with respect to angle theta, with respect to the horizontal, that is 46.0416. Then you have here TBC, which is 4.8621. Okay, so let's focus on this one. Okay, so again, you have here alpha, by the way, alpha. Okay, so again, same procedure. You would have here summation forces along the x-axis is equal to 0. Let's take positive going to the right. You would have TBC is equal to, or TBC times what? Horizontal component cosine of 46, or cosine of theta. Okay, and then you have here also along on the opposite direction, you have TAB times the cosine of alpha. That would be equal to 0. Calculating for TAB cosine of alpha is equal to, you have 4.8621 times the cosine of 46.0416. Okay, so you would have here TAB is equal to, you have there 3.375. Okay, that is tension for sorry, that is messed up big time again. Okay, so let me rewrite that one. That is TAB cosine of alpha is equal to 3.375. Equation 1. Next is summation forces along the y-axis is equal to 0. Let's take positive upwards. Okay, on the upward direction, you have there TAB times the sine of alpha, and then minus, you have there 3, and then minus, you have TBC times the cosine of, or sorry, that should be sine. Okay, times the sine of theta is equal to 0. So, calculating for TAB, sine of theta, or sine of alpha rather, is equal to, that would be 3 plus 4.8621 sine of 46.0416. TAB sine of alpha is equal to, that is 6.5. Okay, kilonewtons. Okay, next is, that would be equation 2. Okay, manipulating again equation 1, you would have here TAB is equal to 3.375 over the cosine of alpha. Now, substituting equation 1 to equation 2, you would have 3.375 over the cosine of alpha times the sine of alpha is equal to 6.5 over 3.375. Okay? Sine over cosine is tangent. Tangent of alpha. That would be equal to what? I'm sorry. That should be, I rushed there. Okay? That should be equal to 6.5. Okay? So, in this case, you would have here tangent of alpha is equal to 6.5 over 3.375. Okay? So, calculating for alpha, alpha is equal to, you have 62.5602 degrees. Okay? Next is, you can now have your TAB. Your TAB is equal to 3.375 over the cosine of alpha, or that is 62.5602. Okay? So, you have here TAB now is equal to, TAB is equal to 7.3240 kilonewton. So with that, you have calculated now all the forces acting on each segment of your cable system. Now, for the reactions, okay, at the supports, again, you can basically take the component. Since TAB here is collinear with RA, same is true with TCD is collinear with RD.